To answer these, I really want to look at the information given and draw conclusions about the other functions that I'm looking for. So for problem 3, I'm going to label this, I'm given the graph of f prime, and I want to sketch a graph for f and f double prime. I'm going to do f double prime first because it is usually easier to draw the derivative of a graph than the graph whose derivative we're looking at. Okay, so if this is f, I want to look at f double prime, and f double prime is going to represent the derivative of this graph, okay? So what I know about this graph is that this graph is increasing up until about negative, I don't know, negative 0.8 or something like that, and then it is decreasing until a little bit past 2, and then it is increasing again. So if f prime is decreasing, I'm just going to sketch down some what I know stuff here. So if f prime is decreasing, then that means that f double prime is negative, okay? And then if f prime is increasing, then that means f double prime is positive, okay? And so then I also have a couple of places where my tangent lines are horizontal, meaning the slope is 0, okay? So that also means that the derivative of f, so f double prime at those points is going to be equal to 0. So at this point right here, I'm putting f double prime right on top of this graph of f prime. So for f double prime, I'm going to have an x-intercept there and an x-intercept here, okay? So since my function is increasing, f prime is increasing, be really careful about saying which function you're talking about. Try not to say the function or it. All right, so because f prime is increasing up until this point right here, f double prime is going to be positive, but it's going to be less increasing because the slopes here are getting less steep. Okay, they're getting less steep and approaching 0. So that means I have something that is decreasing and coming down to 0. Then we have a slope that is slightly negative, more negative, more negative, more negative, but then it starts getting less negative, less negative, less negative, less negative until it gets back to 0, which makes sense if we have something like that. Oh, okay, I kind of missed. You get it. All right. And then we have slightly positive, more positive, more positive, etc. So going this way. So which kind of makes sense here. My graph's a little bit wonky, but I've got what appears to be like a cubic function, so my derivative should be quadratic. So yeah, it does make sense that I would have kind of this quadratic curve, very sloppy, but this quadratic curve here for f double prime. Okay, now for f, now the graph of f prime, let me get rid of these little marks, the graph of f prime is going to tell me about the derivative of f. So what I see here is that since f prime is negative until negative 2 and then becomes positive, well, think about, hold up your hand in a way where your slope is negative, the slope of your hand is negative, and then becomes positive, you should have traced a minimum. So that means I have a minimum on f at negative 2. And then at x equals 1, f prime changes from positive to negative. So my slope changes positive to 0 to negative. So that means I have a max at x equals 1. And then I have another minimum here because f prime changes negative to positive. So f has another minimum. So also at 3. Okay, so that's useful information right there. And honestly, that's really enough to graph. The only thing is, I don't have a height. I don't have a value of f to start this graph at and then build everything else around it. And if we think about it, if all we have is f prime without any information about f, like without it saying f of 0 equals negative 6 or f of 2 equals 5 or something like that, we can't actually put the graph of f onto our coordinate plane. We can just graph a possible graph. So really, I just need to have any graph that has a minimum at negative 2 and 3 and a max at 1, and probably appears to be quartic because, again, this looks like a cubic graph, so that appears to be the derivative of a degree 4 function, okay? But really, if all we have is something about the slope, we don't have anything about the value, so we don't know how high or how low to put these points. So I can kind of put them wherever I want. All right, so I'm going to start with, oops, I'm not going to do that. I'm going to start with my max at 1, and I'm just going to pick somewhere with an x coordinate of 1 and say, yep, that's going to be a max. And then I'm going to have a min at -2 and 3. So at x equals -2, I don't know, somewhere right here, we'll have a min. And at x equals 3, I'm going to put it right here. I don't have to put them at the same height. So, all right, and then I'm going to kind of fill in what is happening in between these. So coming down and then going up and then going down and then up again. All right, so this is a possible graph of f. Yours could look very different. You could take this whole thing, shift it up or down as much as you want, as long as you have the mins and the max in the same x coordinates that I do. Okay. All right, then for this last one here, we are looking at 3 functions. We have a solid function, a dashed line function, and a dotted function, okay? And it says that they are related by derivatives. One is f prime, and one is f double prime, all right? If you haven't already, stop the video, take a minute, and try and look at information about one, like just pick one. Say, I'm going to start with, I don't know, the solid function or the dash function, and say, what do I know about like where this is increasing, where it has a horizontal tangent, where it has x-intercepts, that kind of thing, and look for a relationship and see if you can figure out which one is which. Okay, so one thing that stands out to me when I look at this, and we could go about this a lot of different ways, what stands out to me is that the dashed function is never negative. Okay, that's maybe important information, maybe not. So the dashed is always greater than or equal to 0. Okay. I also see that they're definitely, between the solid and the dashed, there's definitely a relationship. They're definitely related here, like kind of shifts of each other. Like if I take the solid one and I go up 1 and shift it to the right by some amount, by how much? Let's see, that one looks like it has a max right around here by whatever, I don't know, 1.5-ish. I wonder what that could be. Shifted to the right, then they would land on each other. So that kind of has me thinking like maybe sine cosine relationships. But it's not exactly correct. Okay, so let's look at these places right here. I notice that anywhere my x, let's see, anywhere I have an x-intercept on the dashed function, okay, x-intercept on the dashed function means I have an x, nope, not everywhere. Yes, well, okay, at both x-intercepts on the dash function, I do have also an x-intercept on the solid. Maybe I need some more about that. Okay, let's do this. Let's look at the x-intercepts for because there's more of them, for the solid function. All right. And so I'm just kind of thinking out loud for what I'm observing here. So I see these points, all of those points are x-intercepts on the solid function. And then if I look to see what's happening on the dashed function at each of those points, I notice that I have horizontal tangents at each of those points. Okay? So in other words, when the slope of the dashed function equals 0, the solid function has an x-intercept. Okay? So that makes me think that the solid graph might be the derivative of the dashed graph. Okay? I think that's true. So solid is the derivative of the dashed. Okay, and then we got to figure out how this other one ties in. Either the dotted one is the derivative of the solid, or the dashed is the derivative of the dotted. Okay, well, what do we notice about the dotted? The dotted never decreases. Okay, the dotted is increasing everywhere. It does have a couple places where it has a horizontal tangent, like right here and right here. And if I notice, the dashed has x-intercepts at those points, but it never actually goes negative. So the dashed is positive everywhere, which would make sense, or I should say greater than or equal to 0, because it could be equal to 0, which would make sense because the dashed appears to be increasing everywhere. Okay, so I'm going to say that this is my graph F, this is my graph F prime, and this is the graph F double prime. Okay, did you get the same thing I did? In case you are wondering what these actual equations are, the graph of F is x plus sine x. The graph of F prime, the dashed one, is 1 plus cosine x. Is the cosine graph shifted up 1. And then F double prime of x is negative sine x. So we picked it correctly.